I would like to thank everyone that you are attending another FMRI webinar. We have the honor to host Dr. Pu on today's webinar. Dr. Ziyuan Pu is currently an assistant professor in civil engineering at Monash University. He earned his PhD degree in civil environmental engineering from University of Washington 2020. His active research fields include intelligent transportation system, intelligent vehicle, cyber transportation, and urban computing. He serves as a member of Connected Automatic Vehicle Impacts Committee and Artificial Intelligence Committee of American Society of Civil Engineers. And of course, TRP Standing Committee on Visualization in Transportation. He is the recipient of 2020 Excellence in Highway Safety Data Research Award, presented by Federal Highway and Institute of Transportation Engineers. Also, he's a recipient of 2020 Mobility Track Award of Metro Lab Network Student Cup. Dr. Pu, the floor is yours. And also, I would like to thank the WTS FAU student chapter that they put this event together. Thank you.
Okay, hello everyone. So let me share my screen. Okay, can everyone see my screen clearly?
Yes, we can.
Yes.
Thank you. So thanks for the introduction from Professor Kaisen, and I will start my presentation today. So my presentation title is Novel Traffic Sensing Methods and Technologies for Non-Motorized Traffic Monitoring under Challenge Scenarios. So traffic data is a set of quantitative or qualitative values which contain the information of traffic flows of different traffic modes. Lots of sensors and detectors in the real transportation system for collecting real-time traffic data, which used as the input of ITS applications. So basically, the applications perform better if the data is more reliable, efficient, and accurate. And consequently, the entire transportation system will be improved a lot by better performance of the ITS applications. So from this point of view, traffic data is the essential input for transportation system management and operation. And for non-motorized traffic, effective sensing methods and technologies are certainly necessary for multiple implementation scenarios, like the smart infrastructures, like smart crossing system. The system need to automatically detect the pedestrian existence, like who wants to cross the road, and also the automated vehicles, which is required to have the capability of sensing non-motorized travelers. And wrong detection results sometimes could cause traffic accidents with injuries. Like the bottom figure shows the vehicle cannot accurately detect the pedestrian in front of the vehicle, and the vehicles just hit the pedestrian directly, and also generate some injuries. So besides the accuracy, efficiency and reliability are also critical attributes for the sensing methods. Since we only have very small time window for decision making when a warning of potential accident is detected. So usually the sensing system is developed as is deployed as two types of equipment, the onboard unit and the roadside unit. So onboard unit is an essential unit for automated vehicles, which is responsible for sensing environment of vehicles during the trip and provide the critical information to support vehicle control. And the roadside unit is a core part of smart traffic management and control system, and collecting traffic data in like more microscopic level, like the traffic volume, travel time, traffic speed. For sensing non-motorized traffic, we do have several like options of technologies like the computer vision, LiDAR, infrared-based sensing, and wireless sensing. Among among the existing sensing technologies, the vision-based method has been demonstrated to be the most effective method for pedestrian detection due to the fluent information and also the cost-effective features. So we do have several challenges that hurt the effectiveness of radio-based sensing methods. One of them is the low illumination conditions. As it is shown in the right figure, like in the left figure, more than 75% pedestrian fatalities occur during nighttime. And in addition, several special weather conditions make the vision-based pedestrian sensing more difficult, like the foggy weather. And the conditions shown in the two left figures. From the computer vision perspective, when the low illumination or adverse weather condition occur, the texture information of the data become scarce and the contrast become worse. Thus, the sensing accuracy and the reliability is reduced. Um, so to address this problem, we propose a multi-spectral network for pedestrian detection, which is called illumination and temperature-aware multispectral network. And the algorithm not only utilizes the features from visual images, but also use thermal image as one of the input to provide the complementary information. And this is also a one-stage algorithm um, that the required computational resources are more or less. Thus, the efficiency is better than the traditional two-stage algorithm, which is commonly used in previous study. And for the image fusion strategy, like I mentioned before, we proposed to fuse the visual image and the thermal images together. And we use a late fusion strategy, which can further improve the detection accuracy, different from the early fusion and the middle fusion strategies. The late fusion strategy actually like early fusion and the middle fusion strategies concatenate the input images directly. But the late fusion strategy will fuse feature maps after passing through several convolutional layers and conducts separate feature extractions in two streams on all feature levels. And the images can be better fused. So, and in order to further improve the efficiency, one method is like reducing the number of default boxes without modifying major network structure. Um, Generally, more default boxes indicate a higher possibility to cover the target objects like the pedestrians or other types of non-motorized travelers. And usually in the typical SSD network, um, each pixel of the feature map will generate multiple default boxes with different aspect ratios. The number could be 4 or 6, like we just show in this figure. Uh, the the aspect ratio is 4, and in most scenarios of pedestrian detection, the aspect ratio of pedestrian is always less than 1. The bounding boxes, like which aspect ratio is greater than 1, actually do not have a significant contribution to final detection results. Um, In addition, the original video frame aspect ratio is greater than 1. And after resizing the frame shape to a square, the aspect ratio of pedestrian will further reduce. So based on this consideration, finally, we only use the aspect ratio in our proposed network. Like we only use 1/2 and 1/3 as aspect ratios, and the number of default box actually is greatly reduced, like several aspect ratios with the several default boxes with aspect ratios more than 1 is removed. So the required computational resources is reduced. And we demonstrate the proposed ITMN by comparing with several state-of-art algorithms. A public data set is used for evaluation. And the data set contain both visual and thermal images. Besides the overall accuracy, we also evaluate the performance under different illumination conditions, like the daytime or nighttime. And the efficiency is also evaluated in the experiment. The proposed method actually is outperformed all other methods, which demonstrates superiority of the proposed method. And this work has been published in the publication in the Journal of Attribute Transactions on Network Science and Engineering. If you are interested in more details, please refer to the link shown in the bottom of this slide. And another challenge for like vision-based non-motorized traffic detection is as more and more detectors and sensors are deployed in urban area for traffic sensing, the traditional cloud-based system cannot afford data processing tasks, since tons of data are transmitted from the edge device to the same cloud-based computational platform for processing. And also, recently, deep learning-based algorithms achieve considerable improvements in detection accuracy by learning fine-grained features from video frames based on much more complicated feature extractors instead of hand-designed feature descriptors in the traditional algorithms. And consequently, the additional complexity of algorithm structure resulting excessive high computational cost, which certainly hurts the real-time performance of the sensing system. And the scholars and engineers proposed a novel strategy for conducting computational tasks in cyber-physical systems, which is called edge computing. And edge computing is a distributed computing paradigm that brings computation and data storage closer to the source of data. And instead of processing data on cloud server, edge computing system usually process data on the edge device, which are the sensors and the detectors deployed on the road or on the roadside or on the vehicles, and which actually save the cost of data transmission and release the stress of cloud server for intensive data processing. And we do have three advantages of edge computing, like the short latency, strong scalability, and high privacy. However, the computational resources of the edge device usually is greatly limited. So the advanced deep learning method sometimes cannot be deployed on the edge device. Thus, we need to come up with a method like to reduce the required computational resources while keeping the sensing accuracy. Usually, we have several methods to improve deep learning-based sensing method, like simplifying model structure, selecting a smaller models or compressing the models. But the sensing accuracy can be influenced by these methods. So we proposed the quantized neural network for crowd estimation. And in the proposed method, the lightweight convolutional network is employed as the backbone of the algorithm. And all weights of the network is quantized to reduce the complexity. And also, the residual module is applied to reduce the negative impact of model degradation. And with the residual blocks, the model can have more than 50 layers and has a significant improvement in detection accuracy, which actually compensate the precision lost due to model quantization. And we evaluate the proposed model using the public dataset and also compare the performance of the proposed algorithm with 12 state-of-art models. Also, we test the performance for different level of crowd density. Actually, in these figures, we only show like the highest level of crowd density. Actually, more than 300 peoples in one images for these two levels. And the results indicate the proposed method is the best in terms of sensing accuracy and efficiency. This work is published in the conference proceedings of IEEE Smart City Conference, and you can grab more detailed information through the paper, which show while the link show in the bottom of the slide. So in the research, what I introduced, actually we utilize the computer vision technologies for non-motorized traffic sensing. But sometimes computer vision technology cannot work very well. So let's discuss about how we collect traffic data. So basically, we have two different types of data collection methods for traffic sensing. Like the point detection, the detectors sense the physical features of the objects at a single location, and then we can obtain the localized traffic parameters like traffic volume and the localized traffic speed. And another method is the traffic sensing based on the re-identification. Usually, a unique identifier or the extracted visual features is needed for tracking the objects, like the vehicles, pedestrians, at different locations. And by having this method, more useful information we can achieve then the point detection, like the trip trajectory and the travel time. So let me illustrate the advantages of the traffic sensing based on re-identification. So as shown in this figure, one vehicle is driving from S1 to S2, and there is a traffic accident occur in the middle of the road segment. And if we calculate the traffic speed based on the point detection, actually we have two sensors at S1 and S2. And then the average speed would be the average of the localized speed collecting by these two sensors. But the delay caused by the accident cannot be captured by this method. But if we can re-identify the vehicles at these two locations, the average speed would be the distance divided by the time difference of the detection time, and then the delay caused by the accident can be captured. So Actually, re-identification method for motorized vehicles are well developed. Like we can utilize several unique identifiers like the RFID uh, in the vehicle rear and also the license plate number. But for transit riders and non-motorized travelers, still lack of we still don't have like effective unique identifiers for tracking them at different location, and also several other factors impact a lot on the extracted visual features like the illumination, weather factors, and also sometimes the privacy concerns may prohibit the implementation of vision-based pedestrian monitoring system. So, like considering the widely used of mobile device in the world, some of the researchers raised the idea of sensing travelers' mobile device for collecting traffic data instead of sensing travelers directly, which is so-called device-based wireless sensing. And a mobile device is discoverable if the Wi-Fi or Bluetooth function is turned on and it is not paired with any other device. In this case, the device keep broadcasting its media access control address in the air, which is a global unique identifier we can use for tracking the tracking pedestrians and other non-motorized travelers. The basic idea of wireless sensing is we need to have at least one discoverable mobile device carried by a traveler, and the wireless sensor capture the MAC address broadcasted by the discoverable mobile device, and then the targeting traffic parameters can be estimated based on the MAC address tracking. So, however, even MAC address can help with tracking travelers at a different location. It still has three uncertainties that impact the traffic parameters collection. So they are the traffic mode uncertainty. So actually, the travelers in any traffic mode can be, if they have a discoverable mobile device, we can detect them. But the traffic mode, the information of the traffic mode cannot be directly observed through the raw sensing data. So we need to address that problem. Another uncertainty is localized spatial uncertainty. So for each wireless sensor, um, it has a certain detection range. So when a mobile device is detected by the wireless sensor, the exact location within the detection range cannot be known. So when we calculate travel time, usually we use the location of the sensor instead of the exact detection location for the travel time calculation. And the gap between those two locations actually generate errors. And the last uncertainty is population uncertainty. Actually, not everyone has a discoverable mobile device, and not every mobile device is discoverable. So for having a better sensing performance, our proposal method actually address the three uncertainties for non-motorized sensing. Like for extracting the target parameters of like transit riders, actually we do need to address two uncertainty. The traffic mode uncertainty, detection range is larger, actually is larger than the inside space of transit vehicles. And the mobile device outside vehicles also can be detected. Excuse me. And another uncertainty is population uncertainty. So not every passenger has a discoverable mobile device. So we need to estimate the population based on the detected samples. So we excuse me. So we proposed a three-step algorithm framework for addressing these two uncertainties. For addressing traffic mode uncertainty, it is assumed the featured space of passengers and non-passengers who are outside of the vehicles. The features are overlapped, and thus we design a fuzzy-based clustering algorithm. And for addressing population uncertainty, we collected lots of ground truth data at different locations and also take the spatial and temporal features as the input to train a regression model. And the model can map to the population based on the detected samples. To demonstrate performance of the proposed method, we implement the design system, including a customized wireless sensor, uh, which is capable for capturing the MAC address of the discoverable mobile device in surrounding areas. And also it is capable for capturing the GPS information of the vehicles. The customized wireless sensor is installed at the vehicles, and and the proposed algorithm deployed on the remote server. The GPS and the MAC address data is transmitting real-timely to the remote server through the cellular network. And totally, the sensors were installed on 3 transit routes in Seattle. And the proposed method is validated by comparing with several selected baseline models. And it outperformed among all baseline models, and the overall accuracy is about 85%. So these two tables shows the output of the system. And if you are interested in the details, please check out our publication in IEEE Internet of Things journal through the link here. And since lots of reasons, we do need to monitoring like non-motorized traffic by re-identifying travelers at different locations. But like as I mentioned, if we have privacy concerns, the region-based algorithm actually is not applicable. So both actually, as shown in these figures, the multimodal traffic signal control, non-motorized traffic management, both applications require real-time traffic data of motorized travelers. So to extract non-motorized traffic parameters from wireless sensing data, like the traffic speed, two uncertainties are needed to be addressed, like the localized spatial uncertainty and the traffic mode uncertainty. In my study, I utilized received signal strength indicator to correct the errors caused by the localized spatial uncertainty and design a semi-supervised clustering algorithm to identify traffic modes. Um, and this figure illustrates how localized spatial uncertainty affects the traffic speed estimation. The sensor, as I mentioned, the exact detection location within the detection range is cannot be known. So when we calculate the traffic speed, we usually utilize the location of the sensor instead of the exact detection location. And the gap between these two locations actually generate the errors for speed calculation. And the RSSI, which is short for Received Signal Strength Indicator, which is an indicator reflecting the signal strength of the detected wireless sensing frame. Though multiple factors influence RSSI values, distance between the sensor and the mobile device is the most significant one. So these two figures shows the relationship between the ISSI values and the distance. So they all follow exponential functions. The estimated functions can help with mapping the ISSI value to a distance value. And then the corrected traffic speed can be calculated based on the equations shown in this slide. The ISSI measurements and the relative position of mobile device to while the sensor are the required input. So for traffic mode uncertainty, I design and modify the semi-supervised clustering algorithm to identify the traffic modes. As it is mentioned, the feature space of different traffic modes are overlapped. So fuzzy-based clustering is also employed. Usually, clustering algorithm is an unsupervised learning algorithm, and the initialized center of each cluster is randomly chosen, so which may result in a local optimal for a certain data set. And to address this problem, I use a small set of labeled data to initialize the hyperparameters of the clustering algorithm, which will improve the performance a lot. In order to demonstrate the performance of the proposed algorithm, actually we installed our sensor at full location at the campus of Tongji University, which is shown in this figure. And we also collect ground truth data, like the multimodal traffic speed between these locations by using video cameras. And the customized value sensor were installed as a roadside unit, and all the data are transmitting to our remote server real-timely through the Ethernet. By addressing the localized spatial uncertainty and the traffic mode uncertainty, multimodal traffic speed is obtained, and the overall accuracy of multimodal traffic speed is about 85%. And also, it is obvious that the error caused by the localized spatial uncertainty is addressed. The corrected speed is much more accurate than the original speed for all three modes. And also, this work is published in IEEE IoT journal, which is shown in this link. And you can grab more details by reading the paper. And like some of the applications may require more precise pedestrian sensing method. And if we have like privacy concerns, video-based sensing method probably is not applicable. And thus, we also like develop a device-free valve sensing method is to address the population uncertainty of the device-based valve sensing. And basically, we utilize the Wi-Fi CSI as the sensing technology, and the Wi-Fi CSI channel state information is used for uh, uh, sensing pedestrian, and which is another fine-grained signal strength indicator. And usually, we have one receiver and one transmitter for collecting Wi-Fi CSI. And the transmitter keeps sending the Wi-Fi frame to the receiver through the line of sight. Once the pedestrian walks through the line of sight, the CSI would be impacted by the physical body. And in this case, we don't need to have a discoverable mobile device carried by the pedestrian, and we still can sense the existence of the pedestrians. And we also developed our sensing equipment and conducted the experiment in both indoor and outdoor environment. We also test multiple types of antennas, including omnidirectional antennas and also directional antennas with different signal strengths. So we use a bunch of signal processing method to remove the noise of CSI signal, like the Hempel identifier, linear signal interpolation, Kalman filter, and wavelet transform. And in the right figure, after the pre-processing stage, the CSI signal is pretty smooth. Each sudden change in the CSI signal actually is a pedestrian movement. And we use this equation to detect a sudden change in CSI signal. And we found the 100 Hertz antenna improve the performance of pedestrian existence detection a lot in both indoor and outdoor environment. And the accuracy is almost 100%. And for the moving direction, the phase differences utilized for identifying the pedestrian moving direction. And the Wi-Fi CSI has more than 30 phases. The CSI signal with longer waveform is perturbed first, and thus we can estimate the moving direction based on the difference of each pair of signal phases. According to the result, the accuracy is more than 95% in indoor environment, and also above 90% in outdoor environment. The speed estimation is based on the identified start and end time of pedestrian existence. And the evaluation results indicates it is very accurate. And if you are interested in more details of the study, please check the paper publishing ASE ICT conference proceeding 2020, which can accessed through the link shown on the slide. And for the implementations, we have implemented our proposed system and algorithm during the Winter Olympic Games to 2022 this year, which is just ended several days ago. This video shows the proposed our customized equipment for collecting data and processing data, which is edge computing device. And we install this device in indoor environment. And this video shows the demonstration of the proposed system for estimating the crowd density and detecting the social distance among the crowd. So, and also when we feel the distance between the audience is too close, the bounding box will become red color, and the system will generate some warning message to trigger some control strategy. So for the wireless sensing system, we also tested, also implemented in China at Tongji University. We installed over 100 sensors at the campus, and since 2017, and the sensors is installed as a ROSA unit. We also visualize the estimated traffic parameters of the the pedestrians working in the campus, like the travel time and also the point volume. So that's all from me. Thank you very much, and welcome to any questions and suggestions. Thank you.
Thank you. Thank you, Dr. Pu. Everyone at this time, please feel free to speak up for any questions or type in the chat.
Thank you, Mackenzie.
It looks like we have one question, Dr. Pu. Can you just give importance to new versions of tech that will help correct the path transport vehicles?
Yeah, we actually we certainly have like more advanced sensing technology in the future that can help us sensing the pedestrian and vehicles like the LiDAR. But in the previous like time period, the cost of the LiDAR actually limited the usage and the implementations of the LiDAR as a roadside unit. And also for some automated vehicles, the manufacturer cannot afford for like more LiDAR sensing system to have a more accuracy, sensing accuracy. But in the future, I think if the cost is reduced a lot, I think until like recently, I think the cost has already reduced a lot. Probably we can like have more advanced sensing system with like LiDAR technology, and probably we in the future we can also fuse like multiple sensing technology together, like the integrate the data collecting from the video system and the LiDAR system and other like even sonic system. And then I think in the future we will have a better performance for sensing traffic. Hello?
Thank you, Dr. Pu.
Any questions?
How is the wireless thermal image maintained? How often do you have to, I don't know if it works with a battery or...
Actually, we like you mean the wireless sensor, right? Not the wireless thermal camera, right?
Yes.
Okay, so actually for the wireless sensor, we do not use battery as the power resources. For the transit rider system, we utilize the power provided by vehicles. And when we install the wireless sensor as a roadside unit, actually we utilize the power provided by the cabinet. So actually we didn't test the option for using battery.
Oh, interesting.
But I think so. Actually, for only if the target is only for capturing the MAC address, like the wireless sensing, actually the power consumption is not very high. So probably in the future we can test this as an option. Maybe combine the solar panel for providing the power sources. And even so in this case, even in the rural area, we can deploy the system for traffic sensing.
Wow. That's great to know. Thank you so much, Dr. Pu.
No problem.